In this video, we're going to take a look at the 2005 free response questions number 2 and number 3. And in the year 2005, question number 3 was a calculator question. So questions 1, 2, and 3 were calculator questions. So let's begin by reading the prompt and previewing the concepts that are being assessed. One of the most important things that you need to be able to do is to identify the concept that is being assessed in a particular question, because that helps with your proficiency and it helps with your time management. Question number 2. The tide removes sand from Sandy Point Beach at a rate modeled by a function given by r. So the first thing I notice about this function that I would note on my paper, and I don't need it to be underlined or bolded, is that this is the off rate of sand. So it's important that I understand that r represents a rate, even though it doesn't have any kind of prime or anything on it. They're telling me that it's a rate. All right, continuing to read. A pumping station adds sand to the beach at a rate modeled by the function s, which is given as a rational function. And so I would note on my paper that this is the on rate of sand. So reading with your pencil is an important thing. Interpreting the problem is very important. Let's continue on. Both S, RT, and S of t have units in cubic yards per hour. So that validates that we're talking about rates. And we're looking at the time interval from 0 to 6, and that would be hours. At time 0, the beach contains 2,500 cubic yards of sand. So that would be another thing that I would note on my paper. It looks like we have an initial condition here. At time 0, there are 2,500 cubic yards of sand on the beach. All right, the first thing I want to point out, and if you're in my class, you've already seen these annotations and you've been able to read about this. This is a classic in-rate, out-rate problem, or in this case, an on-rate, off-rate problem. Remember, in this situation, the total rate, which I'm sure will be in one of these questions, is always equal to the in-rate minus the out-rate, or in this case, the on-rate minus the off-rate. This is one of the keys to success in these problems, and you should be familiar and recognize when you have an in-rate, out-rate problem. Let's look at question A, and let's just identify the concept that's being assessed in each part. In letter A, give me 1 second here. I'd like to be more precise in my underlining a little bit. Sorry, shapes, that's what I want. Okay. So how much sand, so that right there, that how much is really important, because how much, when I have rates, a how much is an accumulation, and that indicates to me that I'm going to be integrating. So what do they want me to find how much of? How much sand will the tide remove? So we want to accumulate the off rate during this 6-hour period. Now, one of the important things to note is that for question A, the initial condition is not involved. All they want to know is how much sand did they remove from the beach, and we have to indicate units of measure. So letter A is simply an integral, and it's FTC part 1, and we'll go back and look at how to do, well, let's go ahead and do that now. So in question A, we want to accumulate all of the sand leaving the beach, so we start at 0, we stop at 6, we accumulate all of the area under R of t. The calculator is going to do the work. This is not something that you would have to integrate by hand by no means. And it's important to include the units because they told us that they wanted units. We can round or truncate our answer, so we can cut it off at the 5, or we can round and we can go 816. Those are the only two acceptable answers. Of course, you can extend more decimals if you wish. You get 1 point for the correct integral, and every part of the integral must be correct. And you get 1 point for the answer, and that is with units. If you don't put the units, you don't get the answer. Let's go back to part B. I'm going to get my horizontal line again. Letter B, write an expression whose name is y of t that gives us the total number of cubic yards of sand. So now we're accumulating all of the sand on the beach at any time t. So if we want an expression that accumulates all of the sand, Now we want to come back and get that initial condition, because we start with 2,500 cubic yards of sand on the beach, and then we want to accumulate the on rate, and then we want to subtract the off rate, and that will give us the amount of time at any time t. So my function, y of t, is equal to the initial condition of 2,500. I start accumulating at time 0. I stop accumulating at time t. We've talked about in class how we want these variables to be different so that we can substitute in the t for x. You could have two different integrals here. You could have the on integral 0 to 6 s of x dx minus the off 0 to t of r of x dx. So you get 1 point for the correct integrand. That means that you are subtracting the on rate minus the off rate. You get 1 point for the limits. Now, if you had a t here, and you had a t here, and here, and here, they might be forgiving, they might not. We don't know from year to year what the standard is going to be. So get into the habit that if we want to output t, in this case they told us they wanted y of t, that we have a different variable here. It didn't have to be x. It could be another variable. It's not a hard problem, but it can be tricky, and you have to consider that variable disagreement with the t and the x. In letter C, find the rate. So this time we're looking for the rate at which, look at this key word, total amount of sand is changing. So this is when we're going to get the total rate, we're going to need the on rate minus the off rate. So in letter C, y prime, that is the total rate, is equal to s of t, because that's the on rate, minus the off rate. And then they told us the rate at which the sand is changing at t equal to 4. So we're going to do this work with our calculator. And you, let's see, how would you have had this? You probably already had s of t and r of t in y1 and y2. And so now you can tell the calculator on the home screen to find the derivative, which is a math 8 of y1 minus y2 at 4. And if you have trouble using your calculator, please feel free to ask me a question in class or in our Zoom session. Part D. For 0 to 6, at what time is the amount of sand on the beach a minimum? What is the minimum value? Okay, so as we've discussed many times, the extreme value theorem is assessed over and over and over again. We're going to need critical numbers, and we're going to need the endpoints. Of course, the endpoints. The endpoints are given to be 0 and 6, so it's our job to find critical numbers. As you know, critical numbers are where first derivative equals 0 or is undefined. Now, because we're trying to figure out the amount of sand on the beach, we're going to need to set the total rate equal to 0. Now remember, we found the total rate in part C, so that's going to be on rate minus off rate set equal to 0. So the first thing I'm going to show my reader is I'm going to tell them that I know that I have to take the on rate minus the off rate set equal to 0, and I get 1 point just for doing that. Now, if on your paper you already had, or in your calculator, I'm sorry, on your calculator, if you had this in y1, which you likely did, and this in y2, which you likely did, then you go to y number 3, and you make y number 3 equal to y1 minus y2. You turn off y1 and y2, and in y number 4, you put in the x-axis and use your calculator to determine where the total derivative, total rate, crosses the x-axis, and you'll get a value of 5.11786. Remember, you need to store that value. Okay, so you're going to get 1 point for getting that critical number, and it's coming directly off the calculator. Now, to determine, there are two ways to justify yourself. The scoring guide uses the table method, and I'll talk about that, and then I'm going to show you some student work. So, first endpoint is 0, and we already knew that there were 2,500 cubic yards of sand on the beach. Now we're going to use an integral, so we're going to go back to the integral that we wrote in part B. So, because this is how we're going to figure out how much sand is on the beach at any time. So we're going to use this integral 2,500 plus 0 to stored number 5 point whatever that number was. And then we're going to do that to 6, and we're going to find out how much sand is on the beach, and we're going to find out that we find the absolute minimum occurring at that critical number. Now, you probably were able to figure that out when you looked at the graph of the derivative, because the derivative only has one critical number and changes from negative to positive at that particular number. So you could have used that paragraph, what we call the paragraph method, to explain that, and I think a student does that on the next page. So this is what real student work looks like right here. So the student said, I set y prime of t equal to 0, I got my first point. I found that number, I got my second point. Even though they rounded to 3 decimal places, they stored in their they stored in their calculator, and they did use a sign chart. Now, normally we would say, uh-oh, I'm afraid the student's going to go for a local argument instead of a global. But the student's just investigating and saying, I know there's only one critical number, and the sign changes from negative to positive. So we read on. We don't grade the number lines anyway. So then they tell us the story. Since y prime is negative to the left of 5.188 and positive to the right, there is a relative minimum at t equal to 5.188. So far, the student has not earned a point because all they've justified is a relative minimum. The absolute minimum can be this minimum or one of the endpoints. So now they're going to explain why this relative minimum is actually going to be the absolute minimum, and now they brought in the endpoint conversation. So they did the integral again, and like the scoring guide did. Now, if the student, so let's erase some of this, if the student had in their discussion, let's say that you did not want to use the integral, because you really don't have to, where the student said since y is negative, if they had said from 0 to 5.118, therefore the amount of sand on the beach is increasing, and the amount of sand at 5.118 is greater than the amount of sand at 0, they have ruled out the first endpoint in a discussion, in a paragraph, without actually calculating the amount of sand. Then they would need to go on and say the y prime is positive from 5.188 to 6, therefore the amount of sand on the beach is decreasing, and the amount of sand, I think I said this backwards. I think I said that backwards. Y prime is negative to the left, or from 0 to 5.118. Therefore, the amount of sand on the beach is decreasing. If that's not what I said, that's what I should have said, decreasing. Therefore, the amount of sand at 5.118 is less than the amount of sand at 0. The derivative is positive from 5.188 to 6. Therefore, the amount of sand on the beach is increasing, and the amount of sand on the beach at 5.188 is less than the amount of sand at t equal to 6. That would do it as well. Student number 2 took their overall rate. Instead of using the function names, which I would encourage you to do, the student did the on rate. So this is the on rate minus the off rate, and they set that equal to 0, so they get the first point. The student gets the second point for identifying the critical number, but they are not going to get the third point because they have only justified a local minimum, and we were looking for an absolute. They didn't discuss the endpoints, so pay attention to that. And then the third student earned no points. They knew that they were looking at extreme value theorem, but they just didn't know what to do. question number 3. Question number 3 is a classic table problem, and it involves several concepts. So let's read the prompt and then we'll take a look at the table. A metal wire of 8 centimeters is heated at one end. The table above gives selected values of the temperature, T of x, in degrees Celsius. So here's T of x, and T of x is not a rate. Values of the temperature, T of x, in degrees Celsius of the wire, x centimeters from the heated end. So they're heating the wire at one end, and so the temperature is different at different places on the wire, x centimeters from the heated end. The function t is decreasing and has a first, twice differentiable, first and second derivative. Twice differentiable means that t of x has a t prime and a t double prime. Letter A. Estimate t prime of 7. Show the work that leads to your answer. Indicate units of measure. So this is approximating an instant rate using an average. So if we want to approximate the instant rate at 7, which is between 6 and 8, we're going to go one data value above, one data value below, and we're going to show the change in y over change in x. You do not have to show the t of and the t of. You are required to show a difference quotient, and you may leave your answer like this with the units, degrees Celsius per centimeter. You do not have to reduce to the -7/2, even though you have a calculator. A bald answer, in other words, if you only have -7/2, you will not receive credit, and units are not necessary in this problem. They did not ask for units, and they're not counted in the points. In letter B, very direct, write an integral expression in terms of t of x. That means you need to be using t of x for the average temperature, and say it with me. In between, we're going to say average value of the temperature of the wire, meaning average value of t of x. Estimate the average value of the wire using a trapezoidal sum with 4 subintervals. So there's several things. We're going to start with writing our integral. This is assessing your understanding of average value versus average rate of change. And we said we were going to do the average value. So if you come down here to part B, so 1 over b minus a from a to b of t of x, in this case dx. That's the integral, so we're going to get 1 point for that integral. Then the trapezoidal approximation, so let's clear the board up here. And we were going from 0 to 8, so I'm going to do a trapezoid. I know this is I'm just sectioning off. I'm not saying we're doing rectangles. That was terrible. Let's redo that. All right, so we're doing first grouping, second grouping, third grouping, fourth grouping. So they told us to put in 4 trapezoids. And be careful, we have to look at if we have common heights or not. 0 to 1 is 1, 1 to 5 is 4, 5 to 6 is 1, so we do not have common heights. Remember that the formula, you always begin trapezoids by remembering the formula for the area of a trapezoid, which is equal to 1/2 the height times the sum of the bases. B1 plus B2. I'm not going to make those subscripts. You know the formula. 1/2 height, base 1, base 2. So we're going to have to do individual trapezoids, and whether you pull the 1/2 out front factored or if you put it with each one. In the work down here, they put the 1/2 in each trapezoid. So this is base 1, base 2 times height. Base 1, base 2, base 1, base 2 times height. Base 1, base 2 times height. Base 1, base 2 times height, and you do not have to get the 75.6875, even though you have a calculator. Now you do, if you're going to do this, let me be very clear. If you're going to leave your trapezoidal approximation, which I would so strongly encourage you to do, you would not get your final answer unless you had this entire sum multiplied by the 1/8. Remember, we had to do the average value. So however you want to do it, but I would recommend just leaving that trapezoid for a time, if for no other reason, just for the interest of time, but more importantly, so that you don't make a silly, careless mistake, type something in your calculator wrong. 1 point for the trapezoidal, so that would be this part right here. Whoops, blah. Just that part, and then the answer is when you multiply by 1/8. All right, going back to letter C. Another very direct question. Find the integral, and remember this is with a calculator. However, notice what we're integrating. We're integrating t prime, and when you integrate t prime, it gives you t of x. So this is FTC part 1, and then we have to explain the meaning of. So we're going to be interpreting a definite integral. So we have two things, FTC part 1 and interpreting. So if I anti-differentiate t prime, it brings back t, edit undo, t from 0 to 8. And let's look down here, it's much neater. So we're integrating 0 to 8 of t prime. That brings back t, evaluated at upper bound, t evaluated at lower bound. I get the numbers out of the table above. I can leave it like that if I want to and put degrees Celsius, or I can go ahead and subtract. And then the meaning is the definite integral represents the change in the temperature. Now they said the temperature drops. That's fine because it's negative. Or you could say the change in the temperature from 0 to 8. The temperature measured in degrees Celsius, what was that, hours? I forgot already. Centimeters. So let's go back again. The definite integral represents the change in the temperature measured in degrees Celsius from 0 to 8 centimeters, and you don't have to quote the 45 degrees if it's already back up here. 1 point for the value and 1 point for the meaning. Oh, there's a part D. I almost cut the video off. Letter D. Are the data. The first thing that you're going to have to get over is that grammatically that is correct. Students actually stop and think about the grammar is the data, but it's actually are the data because there's multiple data points. Are the data in the table consistent with the assertion that the second derivative is always positive? Okay, so they're saying someone thinks the assertion, that's an assertion, conjecture, that the second derivative is always positive. Can you either affirm or refute this assertion based on what you see here? Now let's talk about the second derivative being positive from the All About Me sheet. There are two things we can take away from that. If the second derivative is positive, t original is concave up. If the second derivative is positive, t prime is increasing. Now, I don't know if we're going to use both of these, one of these, or neither of these, but you need to remember that there are two things that you can use to try to figure this out. Now, when I look at the original function, I might be thinking, well, I have t of x, so I'm probably going to use t of x. But look, we only have 1, 2, 3, 4, 5 points. We can plot those points, but we're not going to know the concavity. So this is actually not the way to go about this problem, and you need to get used to thinking about this situation when you deal with a second derivative. Now, what I do know is that if the second derivative is always positive, t prime is always increasing. So I'm going to use average rates to produce some t primes, because by the mean value theorem, if I can do some average rates, that means the instant rate has to equal these values at a particular time. So again, I'm kind of going back to part A. I'm doing average rates to predict instant rates. All right, now in this work, they just go straight to 2 points that will refute the assertion. So they found the average rate of change from 1 to 5 to be negative 0.575. I'll show you student work in a second. And they found the average rate to be negative 8 from 5 to 6. Well then, if this rate is negative 5.7 and this one's negative 8, then t prime is decreasing, because from negative 0.575 to negative 8, that is a decrease. That means t prime is decreasing, which says, nope, this can't be true. Now, you might not have thought, okay, I know which two specifically to go to. Well, let's look at student work. What a student would likely do is what this one did. The student says if the second derivative is positive, then t is increasing over the interval. So the student found the average rate from 0 to 1, from 1 to 5, from 5 to 6, from 6 to 8. In other words, they just tested, they found all those average rates. And so from negative 7 to negative 5.75, that would be an increase. So that wouldn't break the assertion. But from negative 5.75 to negative 8, that means that t prime is decreasing, so the second derivative can't be positive, and you don't really have to worry anymore once you break the assertion. You do not have to use the words mean value theorem, although that's really what's in play here. And then they made their conclusion. I don't know if I have another student work. Oh, here's another student work. So this student was on the right path. They're calculating average rates. So the student says that the first rate, where do they do that? So from 0 to 1 is decrease 7 degrees Celsius, fine. From 1 to 5, negative 5.75, fine, great. And that's an increase, so that doesn't break the assertion. Then, unfortunately, when they go from 6 to 5, or 5 to 6, I'm sorry, they do a miscalculation. And even though that this is a decrease, there's a point off for the miscalculation. So even though they broke the assertion, they're going to lose 1 point. They're not going to get all 3. They're going to get 2 of the points. Or the first point, but not the second point, I'm sorry. And I do believe when I looked at the scoring guide, I think there were some unit points. I don't remember if I said that there were no unit points or not. Let's go back. Where was that here? Yeah. So you did need units in A, B, and C. So if you missed units in either of those sections, you're going to lose the answer point. But you're only going to lose 1 answer point. You're certainly not going to lose 3. All right, so tune back in for the 2005 4 through 6.